Good. So before we proceed, is there any question from anybody on what we covered last week? Of course, just to confirm that you can hear me, Avilash, you can hear me, right?
Yes, sir.
Very good. Thank you so much. Okay. Is there any question? Okay. So what I will do is that I will do a quick recap of what we covered in our last week's lectures, and then we'll proceed to the second part of this topic. We have mentioned that it is important to have a good meaning correct model of the data before we actually start designing our database. And as we have mentioned that our database is a collection of these tables or relations in relational databases, and we have to have a very good database design. Now, when we say good here for database design, it should be correct and also efficient. And we can do that only when we have a correct data model. And in the context of data model, we said that we will look into this entity relationship model or ER model. And we have seen what are the components of an ER model of data. Also, we have seen how to represent an ER model using ER diagram. And in the lab also, you are given a simple problem where you can come up with its model and then represent as a diagram. We have talked about entities, relationships. We have talked about strong entities, weak entities. We have talked about attributes, different kinds of attributes. We have also talked about the primary key of the entity set or the key attribute. So these things we talked about. For the notations, we have seen standard notation initially, and then we have also seen some very specific notations, and including some notations which are supported by some of the tools. So at this stage, we have a good understanding of how we can model data for any given application. And in the lab, we are given some representative application where we try to come up with a data model and represent that using an ER diagram. So similarly, when you start mm, looking at any system, any software system from data point of view, of course, those will be pretty complex, and it is very important that we first have a uh, good understanding of the different data elements and their relationships so that we can come up with the correct model and represent it as the diagram. Also, as I had mentioned, that it is not necessarily true that we as database designers can come up with always the correct data model. So we, after talking to the end users and various stakeholders, we would get an idea about these different data elements and their interrelationships, and then we'll try to, based on our understanding, represent them as in the form of an ER diagram. But then it is important that we show it to the users, and they will be able to tell us whether the data model is correct, including the cardinalities and participations and so on. Now, assume that we have gone through this process for a few iterations where we first learned the, the existing system, how users view their data, came up with a model, shown it to the users, they corrected it and gave some suggestions. And we then again represented those corrections in the updated data model and again showed it. So after a few such iterations, we now have a uh, data model which we can assume to be correct. But then the data model on its own will not be sufficient, because at the end of the day we have to come up with our database schema, which is this collection of tables. So what we need is that we need this second step, which is reduction from an ER model to relation schemas. So that is what we'll now see. Now the term relation schema, just to refresh our memory is that what we said as the table structure means the table name and the names of the columns, their data types, and so on. So that is called a schema, a relation schema, often called a relational schema. So a table structure is called relational schema. These are synonymous. And collection of such relational schemas makes our database schema. And when we talk about individual instance of a schema, say for example, if we have this table called student with roll number, name, and say department as a relation schema, then a relation is basically an instantiation of that schema where we have some data as rows in that schema. So that becomes a relation. So relation, you can assume that it is a schema with some rows uh, added to it. So that becomes the relation, and then from time to time, of course, the relation can change based on the current set of rows, but the schema remains unchanged unless we for some reason happen to change the schema itself. So we need to have this understanding of the terms relation schemas and relations. So schemas once again are like relation schemas are like the table structures, and relations are the tables along with their contents, and which can change over time, the contents typically, and the schema is likely to be more static. So with that background, let us see what are the steps for reducing any ER model, which is in the form of an ER diagram, to relation schema. Now, entity sets and relationship sets, they can be expressed uniformly as relation schemas that represent the contents of the database. And a database that conforms to an ER diagram can be represented by a collection of such schemas, which is fairly simple, as I have already mentioned. So now, for each entity set and relationship set, we'll see that we'll come up with a unique schema that is assigned the name of the corresponding entity set or relationship set. So we'll have the schema means, as I said, that it has to have the name of the relation schema and also what are the columns. So these also will be having unique names, as we'll see. So first is that let us consider representing entity set. So as we remember that entity sets, they could be strong entity set or weak entity set. If it is a strong entity set, it's fairly simple. Say we have a student as an entity set which had these three attributes: ID, name, and total credits, where ID is the key attribute or the primary key. So that entity set simply will become a schema, a relation schema or a table with the same name as the name of the strong entity set, and its columns will be same as the attributes of the corresponding entity set, and the key attribute that was there for the or the primary key of that entity set will become the primary key of the table. So each table also or a relation schema also has a primary key, which is the same as we discussed in the context of entity sets. Now we'll see that for various such schemas, how to derive the primary key when we are mapping the ER model to the database schema. So when it is a strong entity set, it's fairly simple that the key attribute or the primary key of that particular entity set becomes the primary key of the corresponding relation schema. A weak entity set becomes a table that includes a column for the primary key of the identifying strong entity set. So it is a little different from mapping a strong entity set to a relation schema. What we have is here section has got these three attributes, and all of these three together form, if you remember, what was the name that we talked about? Anybody remembers? For weak entity sets, we did not call it the primary key, but what did we call it? Any,
Discriminator.
right, very good. So what we have is that these three were underlined here. So all these three will be there, and more importantly, this course ID, which is the key attribute for from the corresponding identifying strong entity set, that also will be there as one of the columns. And then the primary key of this relation schema will be made up of this course ID, which is the primary key of the strong entity set, allows us these three different attributes which are underlined here. All of these three will be here. And suppose there was one more attribute which is not here, so something else, okay, that section ID, semester year, maybe we have a name or something, okay, so which is not underlined in this section we can reset, then that also will of course be there as a column, but that will not be part of the primary. So that is what we need to keep in mind. Now for the relationship set, so let us see that there is a little subtle issues, a few subtle issues are there. We have to understand. So when it is a many-to-many relationship set, it's fairly straightforward. Say an instructor to student, as you see on both sides, there is no arrowhead, means it is a many-to-many relationship. So then uh, what we have is that for this relationship set advisor, we'll have a relation schema, which will have this key attribute from the instructor entity set and the key attribute from the student entity set. And because both of them we named as ID, so when we bring them here as columns of this advisor, which is a new table or a new relation schema we derive from this advisor relationship. So the name of this schema will be same as the name of the relationship set, and then its two attributes which will be together forming the primary key of this advisor table, that will be coming from this instructor primary key and the student primary key. And just to make sure that we can differentiate between the two, one we name as the S underscore ID, meaning the student ID. The other we rename as I underscore ID, meaning instructor ID. In fact, here also when we wrote it, we could have written that as instructor ID, and here I could have written it as student ID. So now this is for when it is a many-to-many relationship, okay? And so this is what will be the primary key for these two tables, primary key for this table, which will be made up of jointly from the two primary keys from these two entity sets that are participating in a many-to-many relationship. The term of foreign key will be clear a little later. I will come to that. So now when it is composite attributes. So what we have seen here is these attributes which are here. We simply bring them here as columns of the corresponding table. Now, when it is composite attributes, what we need is that we have to flatten them out by creating a separate attribute for each component attribute. So if name is made up of this first name, middle name, middle initial, last name, and similarly for address, what we'll do is that we will not have any column called name or a column called address or any column called street. Rather, we'll have the columns first name, middle initial, last name, street number, street name, apartment number, city, state, zip, and so on. So what it means is that we'll have this flattened out by creating a separate attribute for each component attribute. Okay. Now, so then if we look at it for the time being, if we ignore this multi-valued attribute phone number, the rest of these will become like this. For this entity set instructor, the corresponding relation schema will be named as instructor, and it will have these different columns. So actually ID should have been underlined. So this ID will be the primary key of this table. So ID, then first name, as you can see, middle initial, last name, then as I said that the most flattened level, street number, street name, apartment number, city, state, zip, and date of birth. And then age we do not need to actually keep here, because that age is something that will indeed be always computed, because it is a derived attribute from the date of birth and the current system date. So we are not going to keep it there, because that value of age will not make sense, because age will be varying all the time, and it is to be always derived from date of birth and some other information, which in this case is the current date. Now, when it is multi-valued attributes, so what we have to do is that for multi-valued attributes, say phone number, as we have said the phone number. So what we'll do is that we'll have to create a separate schema relation schema, and then we'll name it as a inst underscore phone, meaning instructor phone, which will have two columns. One will be this key column from here, and the other will be this attribute. So it will be ID comma phone number, and very importantly that these two together will form the primary key, because for the same ID there could be multiple phone numbers. So if we made only this ID as the primary key of this phone table, then what would happen for one ID, say ID 1, I can keep a phone number 2345, but then if that ID has another phone number 3456, then you will not be able to keep, because once we have kept ID 1 and 2345, I cannot enter again 13456, because this I is repeating. And if we had only ID as the primary key, then that would not have been allowed. But now that ID phone number together is the primary key, means that combination will be unique in the table. So remember this, when we have a composite primary key, it means that combination of those columns, values of the combination of those columns must be unique in the table. So then this combination 1 with 2345 is different from 1 with 3456. Hence, both of these rows can be kept in that table inst underscore phone. So, uh, so that is, so if there are multiple such multi-valued attributes, suppose there was a phone number is multiple, and then there were, say, any other information that was also multi-valued, in that case we'll have separate, say, another attribute, say xyz, which is also multi-valued. Then one such table will have for the first multi-valued attribute, which is ID phone number, and then another one will be for ID that xyz attribute, and in that case ID and xyz for that second relation schema. So that combination ID with that attribute xyz will become the primary key. Okay. So this is what is important. And so what this example, as I said, exactly similar to what I just now mentioned. Okay. Now, a few other things. So is there any question up to this, anyone? Any question? Any doubts? Okay. So if there is no doubt, let me proceed a little bit more. This is something that we need to see, that if we said that it is many to many relationship, okay, then for that relationship we'll have a separate schema, as I said here. Okay, so it is for many to many, we said that we'll have, definitely we need to have a separate relation schema corresponding to this relationship advisor, and it will have not only these two. So that point I need to clarify, that it will have these two key attributes coming here as columns and together forming the primary key. But in addition, suppose this attribute also had, sorry, this relationship also had another attribute, like the date from which this one started, this advisor-advisee relationship started. So that date, that attribute also should be included here as the third column, but that will not be part of the primary key. So let me repeat that when it is many-to-many relationship, and this relationship has got an attribute of its own, then the columns of the schema derived from that relationship set will be the key attributes from the two sides, which is shown here. Along with that, all the attributes that are there for this relationship set, that also will be part of this one of the columns, or one or more of the attributes will become one or more columns in this table. But the primary key of that table will be a composite primary key formed by the primary key from this entity side and also the primary key from this entity side. So that is what you need to keep in mind. But the question is that if it is one to many, then what happens? Okay. So now there is something that we need to think. So let us focus first on the department student. So let us consider this. So let us assume that if it is, say, as you see that department to student, it is one to many. So a department can have many students and a student can belong to only one department. Okay. Now, similar to many, if we created a table, separate table for student department, in that case, what we have to understand is that what will be the columns of that, and then what will be the primary key for that. Okay. So if you see that if we create a table for student department, then similar to many, if we thought, okay, and for the timing, let us not worry about the participation. So in that case, if we made it one to many, then can anyone? So let me repeat what I'm saying. So I have a department and student, and as you can see, it is a one to many relationship. And then, if we wanted to keep a table for student department relationship here, then what do you think would be the primary key for that table? Can anyone suggest? So the question is that this department to student, it is one to many. One department can have multiple students. One student can belong to only one department. And this relationship, student department, if we wanted to make a table only for that student department relationship, then what would be its columns and what would be the primary key? Anyone? What are the possibilities?
Department name can be the primary key.
Name.
Department name.
So the department name, that is
Student
what
ID
is
can be
the
the
key attribute from the department, that would be the primary key, right?
Yeah.
And what will be the columns? So one, of course, will be department name. Very good. And then what other columns will be there?
ID.
ID.
Student ID.
Student ID. Okay. Now, if we keep department name as the primary key, then just think that all of you belong to computer science department. Then how can you enter the rows there in the student department table? So first one say is CS, and then roll number is,
No, sir,
say,
it has to be the other way. Student ID has to be.
okay, right. So very good. So then let us consider that student ID is the primary key, and department name is the other column which is not part of the primary key. Very good. I like that you made that attempt, and that is what I wanted, that you think about it, and immediately will realize that you cannot make that department name as the primary key. But very good answer, that we will have these two, department name and ID, these two together as the two columns, not together, these two will be the two columns of the student department table with ID as the primary key. Very good. That is the student ID as the primary key. Excellent. Okay. Now you see that table has that student department table will have ID as the primary key. Okay. But then for the student table, what is the primary key? Very simple. For the so from the
ID.
ID, right? Very good, excellent. So for the student uh, entity, there will be a student table which will also have ID as the primary key. Now it means what? That student table for a given ID, say one, I know the exact name and I know the exact total credit. Similarly, for the student department also, if we have this ID as the primary key, then for that ID I will know the department name. So you see, if there are two tables which have the exactly the same primary key, so even in the first table, for that particular value of ID, there will be unique values for the other columns. And similarly, for the second table, student department, for the ID also there will be a unique value for the department name. So if that is the case, can you do something better? Instead of keeping the student department table, what else can we do?
We can add a column department name under the student table.
Exactly, absolutely fine. Perfect. So then you see that this is the thing, that the department name I can put as a column in the student table, and then I don't need that extra table called student department. So this is what this particular slide is trying to tell us. Okay. Now this is very good. So you see that for many to many, we definitely have to have that extra table, but for one to many, we do not really need to have this extra table. Rather, what is there, from where this is, for one department there are multiple students, and for one student there is only one department. So that's why from the department side I have to bring the primary key as a column to the student table. So what is important is that in the data model we will not repeat the department name with the student entity set. Department name is an attribute of the department entity set. So which is not to be shown, that is important. It will not be shown as an attribute of the student entity set. But when we derive the table from here, then what we'll do is that we'll add this department name as a column for the table student, which will be derived from the student entity set. So that is something you need to keep in mind. Do not make that mistake. What is also important to see here, let me tell you something. As I said, that there is some subtlety in it. Okay. So here you see that from student, in the relationship it is shown that the participation is total. It means what? It means for every student there has to be a department name. Okay. Now this is something that you need to understand. See this, for this case, when the participation from the student side it is total, it is absolutely correct what we have just now come up with, the solution that you mentioned, that department name will be an a column in the student table, so that for every student I'll definitely know what is the department. Now suppose if the student to student department, this relationship, this participation of student to the student department relationship had not been total, then what would have happened? What do you think? That means for every student there may not be a department. Then what do you think would have happened if we kept that department name as a column of the student table? What
Some rows
would
were
you?
empty.
Yeah. So for that, good. So that will be empty, right? For the students. So there are say 10 students, of which for 9 the department is known to be CS, and because the participation is not total, so say the 10, the roll number 10 or ID 10, the department is not known. So as you said, the department name will be blank for that student, right? That is what you said,
Yes, sir.
or empty or blank. Now
Yeah.
this is this empty or blank. There is nothing like empty or blank. It is called null, NULL. So null is a special value that is kept in tables, which means that the value, as you said, is exactly not known or empty, or so that is what is called null. Okay. So that is different from a space. So it is basically not known. Okay. So then, so it is okay to have that table called student with that column department name in it, even when the participation is not total. But then you have to keep in mind that in that case, wherever for some students we do not know the department, the value that we have to keep as null. Okay. So this is something that you have to always keep in mind. The other possibility was that if the participation, again, if the participation is total, that extra table was definitely not required. We could have kept the department name along as a column in the student table. But suppose this is not total, and then suppose we kept a table called student department, which will have student ID and department name as the two columns and ID as the primary key, and we did not keep department name with the student table, then what would have happened? Let me repeat that if we had the student to student department participation not total, and then we kept a separate table called student department with two columns, ID and department name, with ID being the primary key, and in the student table derived from the student entity set, I did not keep the department name as a column, then what kind of data would you keep in the student department table? Anybody? Is the question clear? Anyone
Yes,
has?
but like, what difference will it make?
Right.
In the earlier case, in we are inside the student table, and there was
Mm-hmm.
the ID column and the department name column. So only these
Mm-hmm.
two columns will get extracted to this relationship set.
This
Mm.
new table, right?
Yeah.
And it will have ID as the primary key. But what kind of rows will you have there? In the take the example when I had say roll number one, his name is say A and some total credit 2, 3, 4. So for all of these 1 to 9, we know the department name, and for roll number 10 or ID 10, I do not know the department name.
Department name.
Then what will you keep in that third table? You will
Only one.
keep, sorry.
Only those who have department will be stored in the table.
Right. So for those 9, we'll have these values, because for the 10, if I again keep null there, then there is no point. I will keep that, I'll remove that table and put a department name as a column in the student table. But suppose that I don't want to have too many such null columns in my design. Okay, so then I could possibly keep a separate table called student department, where I will have the ID and department name as two columns with ID as the primary key, and only and when the participation was not total, then only for those entities of student for whom there is a department name, I'll keep those in that third table, and the ones for which it is not known will not keep there. But just keep this in mind. So this is a possibility. I'm just telling you that this is a design choice, okay, that that I could keep. So that what that would mean is that only the so the what is the difference in these two design is that in this second design we are not letting any column to have null values. Okay, but what will be the difficulty if we keep this third this third table? So when the participation is not total, so instead of keeping this department name as the third column and allowing it to have null values, vis-a-vis this design where there is no column which will be allowed to have null values, but we have this third table with the ID and the department name. So these are the two design choice alternatives, right? So what is the advantage of this second? This is that we are not going to allow any null valued column. Sometimes some people are very finicky about null allowed columns and say that no, null is not a good thing, so we'll not allow any columns to have null values. So then this is your only option left, that you will have this third table, where you will have student this ID and department name only for those students for whom the department name is known. But in that case, what is the difficulty? Any idea? Is the question clear? So the hint is that for any student, how will you know whether there is a what is the name of the department? How will you know that?
We have to see the whole table, and if an entry exists, then we can see the departmentals.
Right, perfect. Exactly. So that means that for the student, all other details you will get from the student table, but to get to know the department name, you have to go to that third table. And for that, what we do is that we have to join the student table with the student department table. And remember, always remember this point, that joining is very expensive in writing these SQL statements for select. So we will try to avoid joins as much as possible. So what I only told you is that these are two possible design alternatives, and one may want to choose that if one is very Puritan, does not want there to be null allowed columns. But if you try to do that, always remember, if somebody gives you that logic, you can always give the counter logic is that, but hey, in that case, you remember you will have more number of joins. I just wanted to tell you that because it is important for you to understand that if you try to go for one kind of design, you will end up having some difficulties. So again, unless one is a real Puritan, I personally don't mind keeping some null valued columns. I would rather have these null valued columns than going for this third table and always trying to join these two to get the result. So I just wanted to sensitize you that these are the possibilities. In many books, sometimes you will see that they will have that second design, but it is good not to go for the second design. That means for all one-to-many relationship, you put that uh, key attribute like the department name to the many side where you have the student table. So to summarize my discussion, I showed you two alternative design choices, but it is preferable that you have this null allowed column and not have the third table. Okay. Now for one-to-one relationship, so what you can do is that, so what you can simply put one key from any one side to the other side. Okay. Uh, so this is, you see, the second bullet is about the null values that I talked in detail. Now for one-to-many, for example, you have a department to HOD, and assume that one department can have one HOD and one HOD can only head one department. Then of course, what you need is that suppose there is an HOD ID or something and a department name, then this HOD ID that you can put as a column either or to the department side. So the department, whatever you have here, like department name, building, budget, and the the fourth column for the department will be the HOD ID, and the HOD table will have HOD ID as the primary key and HOD name and other things, date from which this HOD is active or whatever. So those will stay, and HOD ID will go to the department table, so that for any department you can see the HOD ID and then go to the HOD table to get other details about that HOD. The other possibility is that instead of putting the HOD ID as a column to the department table, you can put that department name as a column in the HOD table. So that because it is one-to-one, even for this HOD ID, you know the department name, which is unique, and you can go to the department table to get to the other details. Or, as I said, that HOD ID, if I put in the department table, then from the department table, from department name, building, budget, and from HOD ID, now you can connect or join to the HOD table to get the details. So that is what is said here. For one-to-one relationship sets, either side can be chosen to act as a many side. So that means that you can actually have this column either going from this side to that side or from the, but that must be only the key column or the primary key column. So as is said that now for this weak entity sets, so we don't need to have any schema for the relationship set. So for this section codes, even if there are some attributes, instead of putting them as an additional schema which will be redundant, so what you could do is that uh, it could actually be put along with the other columns of the table which is generated for the weak entity set section. Okay. So that is what you can do instead of having this. So it is very important that we avoid redundancy, because as soon as you have more tables, like I gave the example of student to department as a separate table, it will always bring in this requirement of having extra joins, and joins are always expensive. As much as possible, we'll try to reduce join, but at the same time, we'll have to have a correct design. We are not going to keep redundant data. So redundancy is avoided, but at the same time, what we are doing is that we are trying to also not bringing in more requirements for join. So that is the basic way one actually maps any ER model to the corresponding relation schema. One point that I would like to mention is that let me tell you this. Okay. Yeah. So let's see. We have any example here or not, I will tell you something. It is not here. So, but let me tell you this point, okay? That I used the term foreign key, okay? So, let me tell you with respect to this example, okay? So, I have this advisor schema, relation schema, which has got these two columns, student ID and instructor ID, okay? So, you see that this advisor schema has got primary key made up of SID and IID. That is fine. But this SID, that a value of SID that will be there in advisor, of course, that must be a value that exists in the student table in one of the rows for the ID value. Similarly, for any row, any IID value that will be entered in the advisor table, that must be a valid ID that is there for a row in the instructor table. As say, for example, if I have instructor ID say 1 and name is say A and some value for salary, and then student say I have a roll number is say, again roll number could be 1 and name could be some DEF and some total credits. Similarly, another instructor could be 2 and some values for name and salary. Student, there could be a value for 3 and some salary, sorry, name and total credit. So you see that these ID and those ID values, they have no relationship as such. But then I can put only those values for student ID and instructor ID in the advisor table. So I cannot put a value of 5 and 6 for student ID and IID, where 5 does not belong, is not a valid value in the student table for one of the rows, or 6 is not a valid value for one of the rows in the instructor table. Similarly, I cannot put, say I had these values of instructor IDs 1 and 2, and students say I had these values of 1, 2, and 3. So in that case, what it means is that the values we can have for student ID can be only 1, 2, and 3, and the valid values for instructor ID can only be 1, 2. So that means your only possibilities are these 1, 1, 1, 2, 1, 3, and 2, 1, 2, 2, 2, 3. No other valid value, no other value would be valid here. Of course, that you may not have all these values because it all depends on which student is assigned to which instructor. If instructor ID 1 has the students 1 and 2, then the two rows will be 1, 1, 1, 2. And if instructor 2 has these students say 2 and 3, then the other two rows will be 2, 2, and 2, 3. So it will be 1, 1, 1, 2, 2, 2, and 2, 3. Those will be the rows that are there in the advisor table. So the actual values that will be there, the combinations will of course will depend on which advisor is assigned which student, or which student is assigned to which advisor. But you cannot, of course, as you can very well understand, put any advisor that is the instructor ID who is not a valid instructor in your instructor team. So this is what is called foreign key. So that is the term that is used in this slide. The second bullet is that this is what is meant by foreign key. So when we talk about relational model, possibly tomorrow, there we'll have a little bit more discussion on foreign keys. Now let us look at some of the other topics. So non-binary relationship sets. So as we have said that most of the cases, the relationship sets are binary, but sometimes there are reasons to have non-binary relationship. So what we have is that this is a ternary relationship where we are having the project, it's a project ID and maybe project title and so on, um, uh, like you are also getting this project. So the third year students are getting the different project titles from the various instructors here in our department. So similarly, we have instructor ID name salary and student ID name total credit. So now we can have this third one, third entity set project. So this project guide relationship actually maps a project to an instructor to a student. So this is what is meant by a ternary relationship. Now the cardinality constants or ternary relationship is a little tricky. We allow at most one arrow out of a ternary, okay, or greater degree means if it is a quaternary and so on. But usually the nature is pretty simple. So we usually have things with lower number of these cardinalities, lower number of these relationships. Like binary is the most common, and at most we have ternary. So so we have at most one arrow out of a ternary. For example, an arrow from project guide to instructor indicates that each student has at most one guide for a project. So if we have this arrow, as it says, from project guide to instructor. So from this project guide to the instructor, if we have an arrow, means that a student can work on a project with one instructor only. That means only one guide for a project. If there are more than one arrow, then there are two ways of defining the meaning. For example, a ternary relationship R between A, B, and C with arrows to B and C could mean two of things. Each entity, each A entity is associated with a unique entity from B and C. That means it is unique entity from B and C with which A is associated, or every pair of entities from A and B is associated with a unique C entity, and every pair of A and C associated with the B entity. Meaning that, again, if we go back here, so if we have two arrows, both to project and student, so whether it means that instructor, suppose there is no arrow to instructor, so is it that one instructor will have a unique combination of a project and student, or it means an instructor and project will have a unique combination for student, or an instructor and student will have a unique combination with project. So there is a lot of ambiguity. Because there are a lot of ambiguity, so typically what we try to do is that we want to ensure that there is at most one arrow, then there is no ambiguity. If there is one arrow, that means the other two will have a unique combination with the entity which has that arrow. So there might be certain tools which allow multiple arrows for ternary relationships, but usually we try to avoid them because that makes things a little bit too ambiguous. Next, we'll talk about specialization and generalization, which is very similar to what you have studied in object-oriented design. In a top-down design process, when we are so first we focus on specialization. We designate subgroupings within an entity set that are distinctive from other entities in the set. We'll take some examples. The subgroupings become lower level entity sets, and they have attributes or participant in relationships that do not apply to the higher level entity set. Depicted by a triangle component level is a relationship, which also you have studied in object oriented design. Instructor is a person, so you can have a person as an entity set, and instructor is a specialization of person. And attribute inheritance, just like inheritance you have studied, a lower level entity set inherits all the attributes and relationships participation of the higher level entity set to which it is linked. But a lower level entity set can have certain extra attributes which may not be there for all the entities in the higher level entity set. So let us take a look at this example. So here what we see is that we have person as an entity set with ID, name, street, city as its attribute, and then ID is the key attribute, and then we have this employee and student. So if it is an employee, so employee is a person, so employee will inherit all the attributes of person. Student is also a specialization of person, so student also will inherit all the attributes of person, including the fact that ID will be its key attribute. But employee has this special attribute called salary, and student has got this special attribute called total credits. Now, this can be overlapping. So in this case, we are saying employee and student is overlapping. So that's what we show as these two separate arrows going to the upper level. And overlapping in the sense, suppose there are some employees who are also studying in the same university. Okay. So in IIT Kharagpur also we have some of our employees doing MS or PhD. So they are employees, and as employees they will have a salary attribute, but as student they will also have total credit. So this is what is meant by overlapping specialization, and we show as two separate arrows going to the upper level. And disjoint, so if it is instructor and secretary, so no instructor can be secretary and no secretary can be instructor. So we show it like this kind of arrows connecting and then going to the upper level entity set. So for instructor, again, we see that there is this rank as an attribute. For secretary, is hours per week of working, which you show as the attribute. Similarly, it could be total or partial, meaning, for example, whether every every upper level entity set must be one of the lower level sets. For example, say a person, uh, whatever we want to maintain in our system, is it necessary that this every person will be either employee or student, or there could be some who are neither employee nor student? If so, then it is partial. And if it is required that every entity of the higher level has to be one of the entities at the next lower level, then it is a total specialization. So if every employee must be either instructor or secretary, or every person is must be either employee or student, then it will be a total. But at any level, if it is not required to be so, then it becomes partial. So this is again similar to our previous discussions on cardinality and participation. So we can have a mix and match of this cardinality and participation. So similarly, here also we can have this overlapping disjoint type of specialization, and with that, this itself could be total or partial. So now what we will do is that we'll stop at this, because this next point that we need to see is that once we have this type of specialization types of relationships, how we derive the database schema from for that. So let me not take it up today. So I'll talk about, there are a few design choices, just as we had those design choices for one-to-many relationships, and I mentioned to you which one has what kind of advantage or disadvantage. So similarly, for representing specialization via schemas, there are a few such possibilities which we will take up in our tomorrow's class. So I'll stop here. Is there any question? If there is no question, I am stopping the sharing and also stopping the recording.